Hello, my name is Travis Sweet. I work as a senior technical support engineer at Confluent. I am introducing today Lu and Heng from Pinterest, and they'll be doing their talk on evolution of real-time user engagement event consumption at Pinterest. Without further ado, Lu and Heng.
Thank you. Hi, everyone. Thank you for joining our session. So today we're gonna talk about our story, our journey of scaling real-time event processing infrastructure at Pinterest. It has been a very interesting journey, and I hope you find something useful and you find some of the ideas that can be applied in your daily work. So the agenda for today's talk. So the first, we're gonna have a brief introduction of what Pinterest is, what we do. Next, we're gonna discuss about the user engagement event processing in general. Then we talk about architecture evolution. We'll do a deep dive into our unified solution, some wins and learns, some ongoing effort, and the last Q&A. So first, what is Pinterest? Pinterest is the visual discovery, visual inspiration, a platform like people from around the world come to Pinterest to kind of shop the products, personalized to their taste, find interesting ideas like cooking recipes, travel plan, home improvement ideas, and also discover the most inspiring creators. The mission of Pinterest is to bring everyone the inspiration to create a life that they love. We are engineers from Pinterest DataEng. DataEng's mission is to create and run reliable, scalable, efficient data platform and services to accelerate the innovation within Pinterest, and also to sustain the Pinterest website and sustain the Pinterest ads business. For me, I have been working on data ingestion platforms, data streaming processing platform built on top of Apache Kafka, Apache Flink in the last few years, and more recently focused on streaming and incremental ETL, hoping to transform the processing paradigm from batch, full data set processing to streaming and incremental processing.
For me, I'm Lu from core data warehouse team at Pinterest, and I mostly work on building up and creating our most fundamental data sets in Pinterest for both like the batch processing world as well as the streaming world.
Yeah. Next, we'd like to do a brief background on the event processing at Pinterest. So this is a typical Lambda architecture. So we have all sort of events, backend events, front-end event, impression event logged to a few common Kafka topics. And then we have batch pipelines. We have first have a data transportation service, move the data from Kafka to S3 as a raw data. And then we have the batch data warehouse ETL to process the raw data and generate the data warehouse source of truth tables. And then all different batch workflows will process the source of truth tables. On the other side, we have the streaming applications directly directly read from the raw event and do all sorts of computations and to power different use cases. Just share a little bit about the scale and data volumes. Every day, we log hundreds of billions of events. That's roughly hundreds of terabytes of data. And the data volume doubles every few years. All these events, whether it's backend, front-end, impression, they all share the same Swift struct definition. One field of the struct definition is event type. We have thousands of event types, and the new types are being added for supporting new use cases. And most use cases actually only need to process a small set of event types. That's the event schema. We have all the streaming application batch workflows to power all different type of use cases, just to name a few. We have from the raw events, eventually we compute signals used in recommendation. We have the raw event compute some derived results directly shown on the product surfaces. And we have a internal and external dashboard for users, for the advertisers, and we have A/B experiments. This is just a few use cases I listed here. Actually, there are more. The event data are actually one of the one of the most important data source at Pinterest. Now let's look at the architecture evolution. So while we have so many use cases we want to support, but initially we have different compute frameworks. Before 2019, we have all sorts of frameworks maintained by different teams. That means different code base. And we used Kafka, just to use the Kafka consumer API to build some like applications. We use Kafka Stream, use Storm, use Spark Streaming. This is all the different frameworks we used before 2019. And one of the streaming strategy was to consolidate the compute frameworks. And after evaluation, we choose Flink. We built a stream processing platform called Zhang on top of Apache Flink. And we manage all the clusters, runtimes. We also provide common libraries and connectors, and we support different APIs. We support the Flink data stream API, SQL, and table API. And also, we extend some of our batch framework called Galaxy to build a near real-time version called a near real-time Galaxy, ARTG. It is built on top of a small set of data stream API, hoping like the people used to write batch workflows can easily write a streaming version. And also, of course, we build all sorts of operation tools like the CI/CD, job management service, and the job deployment. So when we have a platform, like a streaming processing platform, we see more people start to build streaming application. The first scaling challenge we faced is stability. Why this is a challenge? So when we have more use cases, reading from Kafka, so the outbound traffic is much, much higher than the inbound traffic. We're already processing a huge data, right? So it's like hundreds of billions of messages per day. And the outbound, it will be even much, much higher. And we see the Kafka cluster has some like high resource utilization and instability issues. And we made a few observations when we look at those applications. They only need to process a few common event types like click, view, and all this common event are just a small portion of all the events. So the solution we built, the first solution we solve this stability challenge is to build a pre-processing job called the Stream Splitter V1. This job is so simple, just have three operators: source operator, filter, and a sync. The filter will just keep the events of a small set of types that are required by the downstream applications. And just and with this, right, with these solutions, we get a derived topic. And we ask all the downstream applications to read from the derived topic instead of reading from the original large topic. And we have some wins here. So the derived topic is only about 10% of the original topic. So when the job reading a derived topic, they process much less traffic. They require less resources. And also the high Kafka cluster resource utilization issue was mitigated. We solved the first challenge we faced. This is not good actually. So just after a year, the derived topic traffic grew from 10% to 30%. And we have more use cases. So sooner or later, we're gonna face the same issue again. And when we look at the jobs, and they just need to like read a few common topics, read the different event types they are interested, but they have to build a filter to read everything. This is not good. So the solution we come up to solve this efficiency challenge is to instead of create one topic, we create multiple topics, one topic for one event type, and then the application, the downstream application, only needs to process the data they need to process instead of reading a topic consists of all different types and then do filter, and also the logic is so simple. We tried Flink SQL. The job is actually a statement set of multiple Flink SQL statement. And the statement, all the statements have the same pattern. Insert into event type I, select from the source event where type equals type I. So simple. And when you support a new event type, just add another SQL statement. It works pretty well. And the downstream application now only need to read what they need instead of reading other unnecessary data. And they don't need to build the filter logic. And the downstream application require much CPU and memory. We have infra savings. And we found the onboarding is so simple, and we love SQL. But this is still, this solution solves the downstream consumption problem. It's efficient, but we still find there are some issues. Because we just write the job as a statement set of SQL statements, the final job graph is generated by the planner. And we found like the job cost twice as much as the V1 job we built earlier. I think the reason why is we have data, the same data, forwarded to multiple pipelines. So you see the source operator read M messages and need to forward all the messages to each pipeline. And this is inefficient. But at least we solved the downstream consumption problem. Around the same time, we also have another challenge is about the data quality. People who build streaming application used to build the batch applications, and they usually, their batch workflow usually start with reading from the data warehouse source of truth tables. But when they switch to streaming, they have to read the raw data, and they get inconsistent results. And in order to have consistent results, they try to replicate the logic in the batch ETL workflow in their streaming job. Before they write anything about their actual business logic, they need to try to do the filter, enrich, dedupe, all those logic in batch ETL. So the solution to solve the data quality issue is to build so-called real-time data warehouse streams. That's similar to the similar to the data warehouse dataset or source of truth tables. We build the data warehouse streams, and this is built on top of the mini framework I earlier mentioned called NRTG. It is just using a subset of Flink data stream API. So some of the advanced features like the state API is not supported. The job graph is not that complicated. It has a source, filter, enrich, dedupe, and sync. Since we don't have the Flink native state, so we have to store all the deduplication key in the off-heap memory via a third-party library. I think the data is generally good, but we have some issues when we do the job deployment, because when we deploy the jobs, all the deduplication key in the memory will be lost, right? So we compromise the deduplication accuracy. So we build an improved version of the data warehouse stream, and we first need to add the Flink state API to the mini framework. And we rewrite the dedupe operator using the Flink map state to store dedupe key with one-day TTL. And RocksDB state backend to store the active keys, and the S3 to back up the state. Now we solve the problems when the deduplication accuracy was compromised during job deployment. This is, I think this helped to provide a high quality data source for the downstreams. So the downstreams now can, instead of reading the raw data, they can read the data warehouse data, and they have consistent results. That's great. And also when they read from the high quality data source, they have to boost our engagement matrix by double digit. Downstream application, they no longer need to kind of do the enrich, filter, dedupe logic, and their job graph become much, much simpler. And they just need to focus on the business logic. But I think we still found there are some issues with our real-time data warehouse streams solutions. Again, like we shared earlier, the generated data warehouse event still consists of multiple types, and downstream have to read unnecessary data and then do the filtering. This is because of the limitation of the mini frameworks. We cannot do very flexible, like splitting, like the general data, like the job that built on top of the data stream API or table API. And also the mini framework introduces overhead. Supporting a new type is slow. The logics of all the supporting different types are coupled together due to the mini framework API requirement. At this moment, we have two set of solutions. One focused on efficiency, the other focused on the data quality. And the downstream users are often confused what to use. Actually, they want both, right? And for us, for the platform team, we need to maintain two sets of solutions. the cost doubles and the KTL also doubles. So we decide to build a unified solution. And the requirement for this unified solution are efficiency, data quality, data velocity, and KTL. For efficiency, we want to make sure the pre-processing job have very efficient runtime. We mentioned the stream splitter way to the SQL-based job is not efficient. We also have for the data warehouse jobs, there's a lot of overhead introduced by the mini framework. We don't want that. We want to have a very efficient runtime for the pre-processing job. The downstream job, that reading the data sources, they should just read what they need instead of reading unnecessary data and do the filtering. For data quality, the downstream job needs to read high quality data source because we see the value of reading high quality data source. Data velocity, supporting a new event type should be simple. Also, the downstream job no longer need to build unnecessary logic, just focus on the business logic. And we maintain one unified solution instead of two solutions. So for the API choice, so we consider different choice to build a unified solution. Eventually, we choose table API because it is much more expressive than SQL. We love SQL, but some complex logic cannot be expressed easily using SQL. Also, the table API is very flexible. The source and sinks are just register and access as the Flink tables. We can, if we want to leverage some of the low-level features, we can convert from table to data stream. Also, there's no actual overhead. And we want to design a job framework so that we can easily support different event types. For the framework design, we have some thoughts put when we design this framework. So each output stream, we want to, from one source, generate multiple output. Each output stream is generated through a pipeline made up of filter, enrich, dedupe, and sync operators. Pipeline is pluggable and independent from each other so that we can easily add a new type, support a new event type through a new pipeline without affecting existing pipelines. Classes from the batch ETL should be reused to maintain consistent semantics. We use Java reflection to easily configure each pipeline. Also, remember the SQL-based jobs is not efficient. The data needs to forward it to each pipelines. So we do some optimization and we found that side output is very useful. More detail will come later. Then the new solution, we build the unified solution called a Platinum Event Stream. Now I will hand over to my colleague Lu to do a deep dive.
Thanks, Heng. So next I will talk about our unified solutions. We called it internally as Platinum Event Streams, and we'll talk into more details of it. So here is like the very high-level diagram around what this streams is providing and offering. It's providing a very high-quality event streams, taking in our raw event data as the input, and then it provides very standardized event selection, so we can have the most consistent logics with our company-wide standard that we've already built for our batch pipelines for several years. And it also have the event deduplication logics that we want to remove the duplicate events for all our downstreams. And also these streams are also built in a way to optimize for the downstream efficiency. So with this unified solution, our streaming application developers don't have to choose between different offerings like Heng mentioned earlier, as in the past. So, and it also highly simplified our internal streaming use case onboarding flow and process. In the past, our streaming application developers, typically they have to start with questions around event types that they should use when, before they are starting their actual development. They may have the question in mind, for example, I want to use event A as one of my signal. Then what is the correct logic to process it from the raw events? And in these cases, they will have to reach out to each of the individual logging owners or metric definition owners to understand all the details of every single event types. It is a very time-consuming process, especially for the applications that they need a very large bag of events. And with our unified solution, we have our centralized data warehouse team to guarantee the event selections are following the right standards within our company. And the streaming application developers, they can just work with this single team to get whatever they need. It hugely helps them to onboard faster with better quality and efficiency guarantee. And moreover, we are also building a catalog system for all these metrics and event processing and kind of having a centralized platform for them to look up all these definitions. So in the future, we don't even need this single team to take care of all of these questions. And if we go a step closer into the technical aspect, here is the technical architecture of what we are building. So we are still reading the raw events as the input and having a Flink application to do the processing, including event splitting, filtering, enrichment, and deduplication. And eventually, these Flink applications will output all the cleansed event data into different Kafka topics, depending on the types of each single events. And with that, it's hugely improved the efficiency of downstream because every single streaming applications, they only need to take care of the events and data that they really care about. And they can subscribe to a very subset of these events. And apart from that, given the Kafka message have very short retention, so we also persist this topic data into S3 Hive tables. So in the case of downstream applications require backfill for a longer period, this data set will be their choice. And if we go in one more step closer into the Flink application itself, so it reads from the raw event topics, which is represented as a Kafka source table internally. And then we have a splitter operator to filter on the events that we need and split the streams into different downstream sub-pipelines. And each sub-pipelines will do the processing for different types of events, including like enrichment and deduplication, and eventually write to the destination Kafka sinks. And then we'll dig into each stage of this processing in more details together in the next few slides. So the first operator is the splitter with filters. So it does two things. The first one is it will filter out the events that we don't need. And also it will split the stream into different sub-pipelines according to their types. So in terms of filtering, we already have a very well-built metric definition repository that we built internally for our batch processing. And it has the interfaces like filter as a function and like dedupe key creation for each type of the events. So implementation-wise, we are having our Flink application to reference this same metric repo to do the filtering and also deduplication. It helped us guarantee the standardized event selection and having consistent logics with our batch pipelines. And in terms of the splitting logic itself, we also have some interesting learnings to share. Like initially, we built the splitting function with a very generic Flink flat map function, but just very similar to our initial Flink SQL base job that Heng mentioned earlier. So in this way, we have each sub-pipeline to do the filtering for themselves and filter on only the events they need. But when we start with this solution, we observed very severe back pressure and scalability issue when the input traffic is very high. So after more investigations, we realized that with this approach, each sub-pipeline will still have to take in the full copy of the input traffic and do the filtering themselves. So let's say if there are M messages in the input event topic, and each of these sub-pipeline will still have to take in all these M messages and then filter out most of the ones that they don't need. So there was a very huge unnecessary overhead introduced here. And later on, with more investigations, we leveraged the Flink side up feature to optimize this solution. So the site output feature is also designed for splitting traffic into different sub-pipelines. So with the site output feature, the splitter initializes the mapping from each event types to a sub-pipeline tag. And then when every event comes, it will try to emit the event with the tag associated, like the right tag for each sub-pipeline. Then these messages will be sent to the right downstream sub-pipelines. So with this approach and optimization, we only need to read the full copy of the data once and have every sub-pipeline only taking care of the events that they really care about. Given the events we care about is a very small subset of the full copy, the performance was improved a lot and the scalability issue was solved in this way. And after splitting the traffic, each sub-pipeline starts with some enrich functions. It just does some common enrichment for downstreams, like we decoded some commonly used fields and derived some fields from a combination of the input values, and we also enrich the events with some latency information so that downstream applications can use the latency information to determine on if they would need to do different actions in case the latency is high or low. And after the enrichment, we also do deduplication for all these events. So first of all, some of you may be wondering why deduplication is needed here. So we observed that duplicate events exist in our Pinterest row event log. In some cases, the duplicate rates could vary from around 10 to 40%. It depends on the types of the events. And the common causes of the duplicates could be sometimes the user is making repeated actions on our Pinterest app. And it could also sometimes be introduced by incorrect client logging implementation, or the client was resending the logging message due to network issue, etc. So with that, we built deduplication logics on both our streaming and batch systems to filter, remove those duplicate events before having all these events or metrics flowing into our downstream dashboard systems or flowing into the ML systems. And the way we do deduplication here is just by using the very standard Flink stateful function. We have all the events keyed by the user ID and generate the dedupe key for each individual event, and check against the Flink state to see if the events already exist or not and whether we should emit, and then update the state correspondingly. As we are keeping a pretty long TTL here with 24 hours for each of the jobs. So it also has very large state, at the level of 2 to 10 terabytes, depending on different jobs. So we also have some learnings to share here. So although the full state size is at about 2 to 10 terabytes, the incremental checkpoint size for each single checkpoint is actually much smaller at the level of tens of gigabytes. And we also did some evaluation for redeployment and learned that with the large states, redeploying from the checkpoint can save the job restart time from around 10 to 20 minutes down to less than 2 minutes. And it is benefiting from the smaller incremental checkpoint size. So with that, we've already covered all the steps that that the job is doing on the previous slides. Also, additionally, to build the job framework more easier to extend, we also use Java reflection to simplify the job setup. So with the metric repository that we already built for the batch pipelines we mentioned earlier, we also create Flink configuration just with referencing the naming of these event classes. And then the job will look up the corresponding event class with these names with Java reflection when building the Flink job graph. Then we are able to reference all these predefined interfaces during the processing. So it enables us to build a new sub-pipeline with only several lines of configurations. And it also guarantees that our batch and streaming logics are consistent by just referencing the same piece of code. So on the other hand, this new solution also hugely improved our data quality in our streaming world. So our downstream streaming applications typically see around 30% to 40% discrepancies compared to their batch systems in the past. And the cost could be unstandardized processing, non-deduplications, etc. And now we are having greater than 99% match rate between our streaming and batch applications. And also to monitor the quality over time, we also built a daily pipeline to compare like this output against our offline source of truth tables. So for all these Kafka topics output, we dump the data into S3 and compare the stats with our offline Hive tables with internal checker systems and build dashboards and alerting upon that. And also, with all the optimizations we've done, this unified solution is also pretty cost efficient. So previously, we have our efficiency solutions costing around 600 vCores to run it stably. And on the other hand, we have in parallel data quality solutions consuming the same like 600 vCores resource to have it run stably every day. And after we build this unified solution, it's combining both features of efficiency as well as the data quality. And the resource consumption for it is just the same as each individual offering as in the past. So it also consumes like 600 vCores to achieve both of the functionalities. So to conclude, these unified solutions give us a downstream user engagement boost brought by this cleaner data source. And it also highly simplified our downstream streaming applications onboarding flow. And we also achieved hundreds of thousands of infra saving and reduced maintenance costs for like these offerings. And next, I will hand it over back to Heng to briefly talk about some of our ongoing efforts for streaming data lineage as well as incremental ETLs.
Thanks, Lu. So some of the ongoing effort, so many streaming applications onboarded come with the need of managing and govern all these use cases. At Pinterest, we also use Data Hub, like the first speaker in this room talk about the data, the governance. We use Data Hub to manage the batch data catalogs and the lineage. And we want to extend this work to the streaming world. So for all the, we build a catalog for Flink tables, and each Flink table is registered for the external system that interact with the Flink application. We also build a lineage for between the Flink job and the external system. Since we are using the same infra, the catalog infra, data lineage infra under the hood, so we're able to build a unified batch and streaming data governance. This is one of the things we're working on. Another area is we're working on streaming and incremental ETL. So we build solutions on top of DBZM, CDC, Kafka, Flink, Iceberg, and Spark to ingest data in the near real-time fashion from online system to offline data lake. And also we build solutions to support incrementally process offline data in data lake. This is another area I'm focusing on right now. Thank you.